This is part of my answer to Robert Lustig's lecture, which, while very compelling, had a number of errors. And I described it on my blog as having a threat of exaggerating the problems with fructose. But it's also an opportunity because one of the good things in his talk is he emphasized the need to go back to basic chemistry in understanding nutrition. So I'm going to try to follow up in a series of presentations what would be a basic introduction to organic and biochemistry. Now, of course, metabolism is very complicated. You have hundreds of reactions and thousands of compounds, and I'm going to try to simplify it a little bit. If you want to understand nutrition and metabolism, biochemical nutrition rests on basic biochemistry. That in turn depends on the understanding of biomolecules and basic organic chemistry. Now, organic chemistry is actually the chemistry of carbon atoms. And so what that means is that historically it had to do with living systems, but it now includes everything that's made of carbon, including polyethylene, for example. It rests, of course, on general chemistry, which in turn rests on basic physical chemistry, quantum mechanics, and atomic structure. Contrary to what the college myth is, the good news is that organic chemistry is easy. It's freshman chemistry that's hard because it rests so much on physical chemistry. And the additional good news is that you can pretty much jump in the middle in organic chemistry and make some progress. So let me start from scratch. Most people know that the formula for water is H2O. Now, what does a chemist see when he sees that formula? You think of this space-filling model, which shows the oxygen atom bound to two hydrogen atoms. Write that for short with these chemical bonds. Of course, it can be very complicated, and the reason for the nonlinear nature is understood, but we don't need to know that. Let's start simply in organic chemistry with methane. And there's a similar representation. The carbon atom always has 4 bonds, and in methane they're all to hydrogen. This wedge and dot structure indicates the 3D form of the molecule. So the hydrogen is coming out of the paper, and the hydrogen is going behind. Here's a ball and stick model, space-filling model, and an atomic structure. Now, the big deal in organic chemistry is that unlike oxygen, carbon forms many chains with carbon-carbon bonds. So what we have is a series of what's called saturated hydrocarbons. They're hydrocarbons because all they have is carbon and hydrogen, and the carbon, again, always has 4 bonds, and if all those bonds are filled with hydrogen, we say they're saturated with hydrogen. So each of these has names. This is the basic thing you memorize when you do organic chemistry. The number of carbons determines what the hydrocarbon name is. There can be, of course, an infinite number of these, but we're usually restricted to about 12. And the common ones in biochemistry are up to 5 or 6. Anyway, let's illustrate the idea with something that's familiar compound, which is octane gasoline. And here's again a space-filling model, ball and stick model. Remember again that that's the carbon, that's the hydrogen, and there's all kinds of different ways of representing it. The simplest way is the one that we're going to use here, and that is we write each carbon as a formula with the hydrogens, and we attach them with chemical bonds. So here's the secret of organic chemistry. The reason that we can do this at all is that organic compounds have two parts. They have the hydrocarbon backbone and a non-hydrocarbon part that contains the chemically reactive part of the molecule, the functional groups. The functional groups define the chemistry of the compound, and we generalize it to say that all compounds that have the same functional group have similar chemistry. So instead of having to memorize the properties of 100 molecules, we only need one, and we hope we can generalize. The alcohols are the simplest example. So here's the hydrocarbons that we saw before. This is ethane, propane, butane. And the alcohols can be generalized to the general formula of R for the rest of the molecule and this hydroxyl group. So what we've done here is we've taken all of these hydrocarbons and we've added a hydroxyl group. So this defines the alcohols. The popular term alcohol refers to ethanol. There's propanol and butanol. You can see that what we did to name them was to drop the E off the hydrocarbon name and add OL. Guess one physical property, and that is you know that the gasolines, like octane, are water insoluble. They're oily as they get bigger. And by comparison, on the other hand, water does not mix with gasoline. It has what's called a hydrophilic character. So the alcohols, you can tell whether they're water soluble, for example, by the extent to which the molecule is made up of a hydroxyl group versus a hydrocarbon group. So the molecule can get pretty complicated, but we guess that we can predict the chemistry. Haven't told you much on the chemistry yet, just by whether it has a hydroxyl group or not. So look at this extremely complicated molecule. The carbon atoms are indicated by the vertices of the straight line to save handwriting. And because there's an OH group, this is also an alcohol. It's called cholesterol. And the hydrocarbon part, of course, is overpowering, so you know cholesterol is not particularly water soluble. Okay, that's the simplest functional group. You got the basic idea that if you can psych out the functional groups, you'll understand the compound. I'm going to stop here, and we're going to do the next functional group in the next YouTube.